Right. Well, you've seen my title, and I'm sorry I left my co-author's name off the printed program. That was an accident, so I regret. But at any rate, to get on with the... let's see, click this thing.
This one.
This one.
And just one click.
That's one.
Yeah.
Ah, yes. What is magnetostrophy? That's a question that I should explain for my talk and also for the following talk, because the following talk is essentially the same title as mine. This is very interesting. This concept of magnetostrophy goes back a long time. I think it was invented really by distinguished plasma physicist Bryan Taylor, who had a brief excursion into geophysics and then left it again. But he left his mark, because what he did was to say, what happens if you try to solve the magnetohydrodynamic problem of the dynamo for the Earth, and you do it by making the solution of a part of it, the part concerning the velocity field, and you try to do it by getting a simple solution of the dynamical equations while keeping the solution of the induction equation, the task of finding the magnetic field, separate. You can't do anything much about that problem. You have to solve the induction equation. But he wanted a simplified way of solving the momentum equation. So he said, we'll just leave out viscosity entirely. Now that seems pretty extreme things to do, but because I explain why it is not so stupid, because this Ekman number, I should define the Ekman number. There's the viscosity, and there's the rotation of the Earth, the radius of the core. That's the Ekman number, which is the distinguishing parameter that you need to address, and he assumed it was 0. And he also assumed that the inertia force wasn't important either. So this is a second approximation, that the Rossby number, defined by a typical velocity and the rotation again and the core radius again, he assumed that was 0 also. So next, I'm applying it to geomagnetism. What is today's, I think you'd call it, I think you'd probably call it a traditional way of solving the dynamo problem. It has to assume, for stability reasons, that the Ekman number is greater than about, say, 10 to the minus 6, and typically it's 10 to the minus 4 is more usual area that people work in. And geophysical reality is that the Ekman number is like 10 to the minus 15. A tremendous difference, the extrapolation over 10 orders of magnitude. And do you think that will work? Isn't it a fairly unreliable thing to do? And I think that the geophysicists who claim that their models based on Ekman number of 10 to the minus 4 or 10 to the minus 6 are realistic, are very brave indeed. I think the reality may be very different. So this is what I want to address. This is what has caused Bryan Taylor's work to be revived. Bryan Taylor hadn't any idea about these problems of extreme parameters. He just wanted an easy way of solving the momentum equation. And the basic theorem, which is always killing off convection and magnetic field generation, is the Bryan-Taylor theorem. And this Bryan-Taylor theorem says if you leave viscosity out and have slow motions, that these motions will be independent of z, that's the coordinate parallel to the axis of rotation. And the only way you can get a motion like that in a sphere is to have a toroidal motion in the zonal direction. And zonal motions can't create magnetic field. It's the end of the story as far as magnetism is concerned. So viscosity can defeat the theorem, and it does that in an ingenious way. It creates small length scales in the direction perpendicular to the rotation axis, and the length scales h are typically at marginal convection of order E, Ekman number. So the scale of the motions gets smaller and smaller as you decrease E. At the same time, you're having to pump a lot of energy in to maintain such viscous motions. So the Rayleigh number, that's the measure here of the convective drive in the Rayleigh number, that increases enormously, like e to the minus, this is a non-trivial parameter, e to the minus, that a factor of 10 to the fifth. So it is a really difficult problem to get over. So you asked the question, is there any other way of defeating this theorem? And the answer is yes, the magnetic field can do it by its Lorentz force. This can break up this impasse the viscosity leaves you with, and can a dynamo create such a field? It's kind of a nice idea. You have a magnetic field that the dynamo creates just to release heat out of the core, and it helps to cool the core, and at the same time it creates the field that we see on the Earth's surface. So it's really speculation at this stage. You say a convectively driven MHD dynamo is energetically less expensive, because less expensive than a viscous dominated dynamo, because it convects at larger scales. It's energetically less expensive. It operates at smaller Rayleigh numbers. So the conceptual way of solving this is quite different from the usual way these problems are solved at the moment. The traditional way of solving this at the moment is to just solve for the fluid velocity. The target is you have to find the magnetic field, given the fluid velocity, find the magnetic field, and they do that simultaneously. They do that as they do the second thing, which is given the magnetic field, find the fluid velocity. Now, for the magnetostrophic dynamo, which I'm going to talk about, you have to separate these things. You have to do them successively. And so what you do, this is really Taylor's concept in this paper in 1963. Should have been long dead, but it's very much alive at the moment. And the main obstacle in this is that you have to switch there's a practical difficulty. You have to switch from cylindrical coordinates to spherical coordinates, because the geometry is spherical, but the dynamics is dominated by the Ekman, the Coriolis force. And so you have to continually switch over from one to the other, and you switch from these cylindrical coordinates. The cylindrical coordinates, I should mention particularly S, because there's no universal name for its coordinates. The distance from the rotation axis. This is the usual phi, usual z, explained before in these spherical coordinates there. So that's the numerical procedure you have to adopt. And that's what we're trying to do, of course. But meanwhile, we've had some successes in using this method. We've used this method on mean field dynamo models. These are models where you introduce an alpha effect. The alpha effect is a way of producing an EMF which is proportional to the magnetic field. So what we're going to do is look at solutions which are axisymmetric in both U and B. That makes it much easier. The alpha effect also supplies the energy needed to counteract ohmic diffusion, ohmic losses. And so you have to, what we find is that when you make alpha greater than a certain critical value, is R alpha, is the alpha effect Reynolds number. This has to be greater than a certain number to operate, depending on alpha, of course. We just use a couple of models to demonstrate. Here's one of our models. So we go from a common starting state here, and then we go to an alpha greater than the critical value, and you get a solution like this. It grows exponentially, and then it saturates to a steady state. And you can see the greater the alpha, the more rapidly it rises, and more the equilibrium state is greater. And the magnetic energy, which is what we're plotting here, against alpha, against time, that's exponential, and it rounds off and goes, it saturates. This is what we get for the magnetic energy, and it gives you a critical value, which I mentioned before. And this, you know, you have to show colour these days. I mean, it's essential, isn't it? I mean, but you know, what did Gilbert and Sullivan say in the Mikado? It creates what did he say? Verisimilitude without convincing, or I forget it's what colour does. You couldn't believe that. But this is the meridian field, and this is the axisymmetric zonal field in the phi direction. And now let's go to this. This is the interesting one, the velocity. And I think they are interesting. They tell new things. Oh, where have I got to? Yes, here we are. This is I skipped one because we're getting short of time. But what's the velocity going? There's a period of intense activity here, but outside the velocity is purely zonal. And this is a surprise compared with what traditional models say. It's not really a surprise because we've got no viscosity. And this is the way the subject's going, in my opinion. The traditional methods, which have these large viscosities, tell you a lie. They tell you that the models create motions and fields that are typically equal for colloidal and toroidal bits. But it's not like that. In these models, the toroidal field is much larger and the velocities are much larger. Well, here's the... How am I doing? Go on time. I'm good. 2 minutes, yeah. Well, I'll just say this is a Terrorization test. This is a test showing how accurate our calculations are, just to convince you I'm not showing you rubbish. This is a thing, an integral, which says Taylor's condition, which is a vital thing in this business, is satisfied compared with the modulus for the integral. So this should be 0, and this is the modulus for the integral. So you compare the integral and the modulus, I should say, and if you've done a good job, this one should be much smaller than this one. It is by a factor of 10 to the 4, approximately. So I think we've done a good job on that. And I just got to the conclusion section now. For the first time, then, we've got these solutions. I've got a couple of references here. I've got the volume numbers modelled up there. The second one is just coming out now, and it can be read on, this is the main conclusion, that the velocity differs strongly from what today's computer models say they should be. And I think the future will show the same thing happens to 3D convective magnetostrophic dynamos. We have to explore parameter space, but the effect of the inner core will be probably very great. So we haven't got an inner core in our models. Okay. Sorry.
Time for a quick question.
I flummoxed everybody.
Yeah.
Paul, when will this transformation happen from the viscous dynamos to the magnetostrophic?
How do you mean will it happen? When will somebody do it? Well, we have to walk before we can run. And we've done a simple thing first. In the future, we'll put convection in, and we'll get three-dimensionality then necessarily, and then we'll also put in the inner core subsequent to that. You know, it's all step by step.
That's a follow-up. If you put viscosity in, could you actually reproduce the numerical model?
Oh, no, I couldn't do that. No, I couldn't do that.
Let's thank the speaker again. Thank you.